What is a continuous random variable? Well, a continuous random variable is a random variable that can take on a continuum of values. So their support is generally an interval or a union of intervals. Here's some examples of continuous random variables. Let's say the time between radioactive particle decays, say of polonium, which I used in an earlier example. Previously, we were looking at the counts of the number of particle emissions that were observed for a sample of polonium. Well, what if instead you were keeping track of the time between particle emissions? The time between emissions would be a continuous random variable. Or how about the time between earthquakes or the time between Mr. Whisker's Instagram posts? All of those are continuous, with support being all non-negative real numbers. Another example might be the GPA of a randomly chosen student. So that can be any number between the closed interval from 0 to 4. So let me introduce now probability density function. So we say that a function f of x is a probability density function if it satisfies two properties. It's non-negative at every point, and the integral over the entire real line of the function is equal to 1. In other words, the total area beneath the function must add up to 1. So let's look at this example right here. That's an example of a probability density function. Let's say it represents GPA. Okay, so let's say that this is the probability density function. That's my abbreviation for probability density function for the GPA of a randomly chosen student. You can see that its support is from 0 to 4 because the function is 0 outside of the support. And the second defining property of a density function states that if I found all the area that lies underneath the curve, it would add up to 1. You can also see that the function is non-negative everywhere. And here's how I interpret probability density functions. When they're larger, they indicate regions where the random variable is more likely. Imagine if you took all the area that's underneath the curve and you randomly chose a position in this yellow area. Well, maybe you randomly chose here or here or here or here or here. You can see that the regions for which the function is larger have more area underneath them, hence are more likely to have a point chosen in them. So the x value that corresponds to a particular value of this random variable would be the x value that lies underneath it. So thus, you can see that x values closer to 4 appear to be more likely for this random variable than those that are close to 0. And on the other hand, x values outside the support have 0 probability because, well, there's no area underneath the curve in those regions. Oops, I just realized I didn't finish my sentence. A randomly chosen student. There we go. Something else I can point out about this picture of a PDF right here is it doesn't have to be continuous. Right? Like this curve is the PDF of a continuous random variable, but the curve itself is not continuous. right? It's got a discontinuity right there, 0. It also has one at 4. That's fine. That can happen. We would say that this is a piecewise defined function. So remember what's continuous here. X, the GPA, that's a continuous random variable. The probability distribution of X is actually a piecewise continuous function that actually has some discontinuities at 0 and 4. Okay, so every continuous random variable has some corresponding PDF, which necessarily satisfies those two conditions. And we could take as the definition of the support of the random variable as the points such that f is 0 outside the support of x and f is positive on the support of x. So you can take that as the definition of the support. You can see in this picture here that the support is from 0 to 4. Okay, now how about the probabilities? Here's how we define the probabilities. If x is a continuous random variable with probability density function probability density function f of x, then the probabilities are defined as follows. The probability that capital X is between A and B is the integral of f of x from A to B. So whereas previously we defined probabilities using sums or discrete values, now we must necessarily describe them with integrals. A couple points of order, or actually, hold on. So let me now draw a picture that represents the probability that x is between A and B. Let's say there's A and there's B. Then this area right here is the probability that the GPA of a randomly chosen student is between A and B, okay, where capital X represents the GPA of a randomly chosen student. And necessarily, the entire area underneath this curve must add up to 1. That always has to be the case. What would happen if I changed the value of this probability density function at a single point? So let's say that I put a hole in this graph and I changed the value at 1 to be up here. Well, guess what? I didn't add any area to the graph because there's no area underneath a single point. So the probability that a continuous random variable is equal to some specific number A is always 0. This is kind of counterintuitive, but it means that the probability of any specific value ever occurring is always 0. Yet somehow, nevertheless, in total, you can have non-zero probabilities. But you can visualize this property by observing the fact that no area lies beneath a single point. And as a result, if you ever change the value of f at a single point, that does not affect any of the probabilities. Okay, all the areas are all still the same. So if this PDF represents the GPA, or the PDF for a GPA of a randomly chosen student, what then is the probability that this randomly chosen student's GPA is 3.7493? Well, according to the new properties of of PDFs, this will necessarily be 0, as it will be for the probability that x is equal to any other particular number. Okay, cool. So moving on. Here's our formulas for the mean of a continuous random variable. The mean, or expected value, or expectation value, is defined as the integral of x multiplied by the probability density function over the entire real line. The variance of capital X is the expectation of the square of the difference of x from its mean. Okay, so the mean is mu, and if we take the difference between x and the mean and square it, and then integrate that against the probability density, that's our formula for the variance. As usual, we take the square root to get the standard deviation, the square root of the variance, that is. So here's a compare and contrast between the discrete and the continuous formulas. For the probability that capital X is between A and B, in the discrete case, we just sum up all the probabilities that correspond to that outcome or that event. And in the continuous case, however, it's an integral. Similarly, so this sum in the discrete case, kind of imagine that it becomes an integral like that. And similarly here, so the sums turn into integrals. The formulas for the variance are, or for the standard deviation, are the same, at least as they relate to the variance. So here's an important calculation that will come in handy, will be used many times. There's another way to write the variance of a random variable, and actually this goes for any random variable, discrete or continuous. So check out this calculation. According to the formula for the variance is the expectation of the square of the difference between x and the mean mu. And mu, by the way, is the mean, but it's just a number. It's some number, right? So given this random variable, its mean is a fixed known number. So let's expand out this square by distributing out the terms. We'll get an x squared and a 2 mu x and a mu squared. So then we have an expectation of a sum. Well, we know that that will be the sum of the expectations, right? The expectation is linear in that sense. So I'll get an expectation of x squared. I'll get an expectation of this term, but you can pull the 2 mu out in front, as I did. And I'll get an expectation of mu squared, but mu squared is a constant. So the expectation of a constant is just itself, so we get mu squared. Okay. This expression can be simplified further because expectation of x is mu. So this term becomes negative 2 mu squared. And then I can combine the mu squareds. I have a minus 2 mu squared and a positive mu squared, which altogether gives me minus mu squared and e of x squared in the front of the expression. So to summarize, the variance of a random variable is the expectation of x squared minus the expectation of x quantity squared. This is a very useful formula, and it will be used many times repeatedly. It's particularly useful for the purpose of computation. And in particular, in the case that we're looking at continuous random variables, you can write it using integrals as such. Okay, so let's get to some examples. how about, suppose that x is a random variable with density given by e to the negative x for x non-negative, or for x positive rather, and 0 otherwise. So here's the graph of this probability density. You can see it 0 to the left of the origin, and it's this decaying exponential to the right. So observe what the integral of f should be, or is. What should it be? Here, so by the way, you should try pausing the video and figuring out the answer to these questions yourself, and then unpause it and you can watch me do them and see if you got it right. So this first question, we actually already know what it should be before we even do the computation. It should be 1, because that's one of the rules for probability density functions. But let's actually do the computation and verify that it actually is 1. The integral of f from negative infinity to infinity, well, the function is only non-zero when x is non-negative. So right off the bat, I can disregard the integral over negative x values, and I'm just left with the integral over positive x values. And let's see, so this is not that hard to integrate. That's negative e to the negative x evaluated from x equals 0 to infinity. At this point, I want to remind you of the method of improper integrals, because we're asked to evaluate a function at infinity. So technically, you're supposed to do that as follows. You would write that as, well, here, let me plug in. In fact, let me first get rid of this annoying minus sign, and let me just write it like this. So I'm going to get e to the 0 minus, okay. Now, the part about evaluating the function at infinity technically should be written as a limit. So I'll write that as the limit as, let's say, t goes to infinity of e to the negative t. In order to see what that is, it might be helpful to look at the graph of e to the negative x. Nope. So there's the graph of e to the negative x. And you can see that when x gets close to negative infinity, the graph is very close to 0, right? It's super small. So for that reason, this term is equal to 0. So we get 1 minus 0, or 1, as we are supposed to. How about the expected value of x? So the expected value, or the expectation of x, aka the mean, is the integral from negative infinity to infinity of x times f of x dx. Since the function is 0 when x is negative, I can just chop that part of the integral off, and all I'm left with is the integral from 0 to infinity of x, and in that region, f is e to the negative x. Remember how to solve these? This is an integration by parts problem. So let's let u equal x. So du is dx, and let's let dv be e to the negative x dx. So v will be negative e to the negative x. And you can see that right here, I've got a dv, and right here, I've got my u. The integration by parts formula, if you recall, was that the integral of u dv is uv minus the integral of v du. So we get, let's see, x times negative e to the negative x from 0 to infinity minus the integral from 0 to infinity of negative e to the negative x dx, according to the integration by parts formula. Okay, let's see. So in order to evaluate this term, when I plug in infinity, I guess I better use the limit again. So that'll be the limit, say as t goes to infinity of t times, I guess, negative e to the negative t. And I'll also have a minus 0 times negative e to the negative 0. And then minus, minus, oh, this is minus, minus, mix up plus. Plus negative e to the negative x from x equals 0 to infinity. Okay. For this term, where I have the limit, in order to evaluate that, we could use L'Hopital's rule. So t e to the negative t is the same as t over e to the t. And we're letting t go to infinity. So this fraction right here is of the indeterminate form to which L'Hopital's rule applies. And it says that, here, let me just remind you. So recall that the limit of, let's say, f of x over g of x is the limit of f prime over g prime. When it's of the indeterminate form of infinity over infinity or 0 over 0. So thus, I can take the derivative of t over e to the t, and I'll get 1 over e to the t. One over e to the t. And I have a negative sign. I guess maybe I can put that in front, actually. Okay, let's see. And then for the next term, oh, well, that's 0 times e to the 0, which is just 0. And then for the next term, in fact, I already did this evaluation in the last problem. That ended up being 1 minus 0, which is just 1. Okay, for the first term, now you can see that, well, this term is e to the negative t. We actually already discussed that limit in the previous calculation, and it was 0. So this whole term becomes 0. And the only non-zero term is this one. So we get 1 for the expectation value. Okay. Any questions? Cool. For the variance, let's see, do I want to do a whole variance calculation? I'll at least say what it is, like what the formula is. The variance is, in general, the integral of x squared times the probability density. In this case, it would then be the integral from 0 to infinity of x squared times e to the negative x dx. Okay, now, I'm not inclined to do this right now, but you should, and I'll just tell you what the answer ends up being. It ends up being 2, apparently. So you should try this. And if you do it right, you'll get 2. finally, the probability that x is less than 5 is the integral from negative infinity to 5 of the probability density. So there's no area below 0, so that just ends up being 0 to 5 of e to the negative x dx. So that's negative e to the negative x from 0 to 5, which ends up being 1 minus e to the negative 5th, which is about 0.99, say 0.993. Okay, cool. So I've got another problem on caffeine concentrations in coffee, which I'm going to answer in class, but I can at least say what the problem is now. So a well-known coffee retailer performs quality control testing on the concentrations of caffeine in their espresso. You can tell I was drinking coffee when I wrote this question. So they find that the caffeine concentrations in milligrams per milliliter of randomly selected batches of their espresso have a density of f of x equals c sine x when x is from 0 to pi and 0 otherwise. So if you plot this density, it looks something like this. C is a constant, but the first question I ask of you is what's C, okay? So to answer that, remember, the total area underneath the curve better be 1. And it's 0 outside 0 to pi. And let's find what the expected caffeine concentration of a randomly selected shot of espresso is. I hope it's high. And could you have guessed what the expected value should be without even doing any integrals? And how about the standard deviation in caffeine concentration? So that'll take a little bit of work. You might need to integrate by parts. And finally, let's find what we would call the 90th percentile. That is, what caffeine level corresponds to what caffeine level is such that it is higher than 90% of the coffees, of randomly chosen coffees. 90% of shots of espresso from this manufacturer have an espresso level that is less than the value that I'm asking for here, which would also be called the 90th percentile. So I'll answer these questions in class, but you should try them, see if you can do them, and then you can see if you got it right in class. Okay, that's it, folks. Thanks for watching. See you soon. Hi, folks. A quick correction to the video that you presumably just watched. Right after I recorded it, I was looking at what I just wrote, and I realized I made a mistake, and that was on the variance part right here. So do you see what's wrong with what's written? Where's the mistake in this line? It's not true. The first equation, that's not true. That's only true if the mean was 0, but it's not. So let me erase this. This is not true. And let me replace it with what is true. What is true is that the variance of x is the expectation of x squared minus the expectation of x quantity squared. So that is the integral from negative infinity to infinity of x squared f of x. By the way, this is also called the second moment of x, and that's actually what I had written down. But minus, let's just call it mu squared, and we actually already figured out that mu was 1. So there's mu right there. So anyway, what we should have is the integral from 0 to infinity of x squared e to the negative x dx minus 1. that will end up being the variance. And you should try it. Go ahead and do it. And if you do it right, you should get a variance of 1. Okay, cool. Thanks. That's it. Suppose that a well-known coffee retailer performs quality control testing on the concentration of caffeine in their espresso, and they find that X, which is the random variable which represents the caffeine concentration in a randomly selected batch of espresso, has the following continuous density. So its density is equal to C sine X when X is between 0 and pi and 0 otherwise. C is some constant, which is as of yet unspecified. The first question is to figure out what little c is. Okay, so problem 1, what's the value of little c? Can someone tell me what fixes the value of little c? Something has to be 1. Okay, I see Justin said it. So the integral of any probability distribution must be 1, always, by definition. That's the rule. So that allows us to determine what c must be. So we set 1 equal to the integral of this probability distribution. This is called normalizing, by the way. Pretty common calculation. So according to the formula, this ends up just being 0 to pi c sine x dx. I can pull the c out in front. Integral of sine is negative cos. That's c times, what is it? 1 plus 1, which is 2c. So apparently c is 1/2. And actually, we can take a look at the distribution. So this is what it looks like. And yeah, so after fixing what c is, so we see apparently that f is equal to 1/2 sine x, at least when we are between 0 and pi. So having chosen c, we now have area 1 underneath the curve, which is good. Okay, the next question was to find the expected caffeine concentration of a randomly selected shot of espresso. So we're asking for the expectation value of our random variable. Let's see. So expectation x is the integral from negative infinity to infinity of x times f of x. That's our new expectation value formula. In this case, the support is only from 0 to pi. So we'll get 1/2 sine x times x dx from 0 to pi. So this is another integration by parts calculation. And let's see, I can solve it by setting this x to be u and sine x dx to be dv. So let's let u equal x. So du is dx, and dv is sine x dx, which means v was negative cos x. And I'll get, let's see, so u times v is x times negative cos x. And then minus v du actually turns into a plus integral of cos x dx. So I get 1/2 pi minus 0 plus the integral of sine x from 0 to pi, but that's just 0. So I get pi over 2 as my expectation value. If we look at the graph, pi over 2 is right there where the peak is. What are some words that describe this distribution? Symmetric. Good. Yes. So note that the distribution here is symmetric. What's another word that describes it? It is a continuous distribution, sure. Someone said normal, so it's not exactly, but it is kind of bell-shaped, we might say. And someone said unimodal. So it is unimodal and symmetric. Which tells us, for example, that the mean and the median coincide. And in fact, we could have used that then to just see what the mean was by looking at the picture. So I just want to point out that you could have also done this calculation using symmetry. Okay, any questions so far? Okay, so I'll do the standard deviation calculation. The standard deviation, actually, hold on a second. Let me pose the class a question. Let's see if anyone already did this. Yes or no? The standard deviation is pi over 2. Yes or no, folks? Just hit the yes or no button. Okay, so let's see. The standard deviation is equal to, well, in fact, let me calculate the variance first. So the variance of x is the expectation of x squared minus quantity expectation of x squared. Let me just do this term. It's the so-called second moment. So this will be the integral of x squared f of x, which will be the integral from 0 to pi of 1/2 x squared sine x dx. And again, I'm going to have to do an integration by parts. So let's let u equal x squared. So du is 2x dx, dv is sine x dx, and v will be negative cos x. And with those substitutions, we will get, let's see, x squared times negative cos x minus negative is plus 2x cos x dx from 0 to pi. And now you see we have to do a second integration by parts. So now for this one, let's let u equal x. And dv is cos x dx. So what's that make the sine? Let's see, pi squared minus 0 plus 2 times, okay, uv is x sine x minus v du is minus the integral of sine x get pi squared plus 2 times, okay, that's pi times 0 minus 0. Integral of sine is negative cosine. So that's a plus. Am I getting my minus signs right? Yeah, okay, plus cos x from 0 to pi. Get 1/2 pi squared plus 2 times negative 1 minus 1. It's cosine pi minus cosine 0. So altogether, get 1/2 of pi squared minus 4, or pi squared over 2 minus 2. So that was the expectation of x squared. I can now get the variance. Yeah, so I'm almost to the variance. I just need to subtract off the mean squared. It's pi squared over 2 minus 2 minus u squared. So pi over 2 quantity squared. This is pi squared over 4 minus 2, which is about 0.46. And actually, what I really want is the standard deviation. So the standard deviation will be the square root of that. So about 0.68. Okay, so that's my standard deviation. It's not pi over 2 as I posed at the beginning of this calculation. And you can visualize the standard deviation, by the way. So here's a way to think about the standard deviation. If you picked a bunch of random points in this area, then the standard deviation of that set of x values would be the one that we found, approximately. So it's a typical distance between points in this distribution. So let's see, it was about 0.68. So that goes about this distance on either, say, on either side. Any questions so far? Okay, the last question I asked was to find the level that's above 90% of randomly selected espresso shot concentrations, caffeine concentrations. What's another name for this number that we're looking for?
The 90th percentile?
Yes, good. So i.e., what's the 90th percentile? Okay. So let's see, can someone who has not yet offered an answer volunteer how we could find the 90th percentile? We want the number, let's see, it'll probably be like right around here. Such that 90% of the area lies to the left. How do we find it? So let's make this a yes or no question. Will it be the integral from 0 to 0.9 pi of the distribution? Yes or no? Yeah, no. The problem is because this thing's not flat. It's not linear. It's not a linear response. Okay, no. So how do we find it?
We set the integral to equal 0.9.
Okay, good. So let's set the integral to be 0.9 and set the upper limit to be this as yet to be determined number. Let's call it t for the moment. So we want 0.9 to be the integral from to equal the probability that capital X is less than t. But that, by definition, is the integral from negative infinity to t of f of x dx, which is, since f is 0 outside 0 to pi, you know this will be the integral from 0 to t of 1/2 sine x dx, which is 1/2 negative cos x from 0 to t, which is 1/2 of 1 minus cos t. So apparently 1 minus cos t is 2 times 0.9. So cos t is negative 0.8. And we can figure out what t must therefore be using the inverse cosine or arc cosine, whatever you want to call it. All right, apparently t then is arc cos of negative 0.8. We'll just use Desmos real fast. .49 or 2.50 actually. Okay, so this comes out to be about 2.5, which looks about right according to our picture. Right, it should be just below 3. Yeah. So right there should be about 2.5. Cool. Okay. So that wraps up this problem. Any questions? Okay. So did you all look at some of those review problems that I posted on Canvas? Wow. I finished them. Oh, crap. Okay, nice. We got one student who's on top of it, and how about everyone else who all who all looked at them? Does anyone have questions on specific problems? So where were they? These one. Oh yeah, there's just 4 of them. And actually the 4th one is not really a very long or serious one. So it's really just the first 3 that are worth doing. But yeah, they're all kind of tricky. So as far as test problems go, these could appear on the test, but they would be like the harder problems on the exam. Okay, so why don't you all let me know which one y'all's interested in.
Professor,
Oh, sorry, you can go ahead.
this is not a specific question for this midterm, but in general in this class, are midterms going to get harder and harder, or is it going to be about the same difficulty as this first one?
I don't know. It's hard to say. Yeah, I really can't say.
Okay.
I would guess they get harder, but maybe not. The material at the end of the class does get tough. You know, what with like analysis of variation and all the inference stuff. It is kind of famously hard, but that's more statistics statistics-y type stuff, whereas this is more probability type stuff.
Got it. Thank you.
It'll probably vary student by student depending on how familiar you are with this stuff. Okay, so let me see if anyone had questions on specific ones of these. Okay, so Alphonse was asking about 3. And did anyone else want to ask about any particular? Okay, so let's check out 3. Snake eyes. Yeah. So problem 3 is as follows. Numbering system for OneNote is messed up. Okay. So 2 dice are rolled in the game of craps, and you look at the result of the 2 rolls. And it's the 2 numbers that you get that determines like whether you win or not. And if you get a pair of 1s, it's called snake eyes. So what's the fewest number of tosses you have to perform so that the probability of getting at least 1 snake eyes is at least 50%. Right. So like if you did say, I don't know, 10 tosses, you could find the probability of getting 1 snake eyes or 2 or 3 snake eyes. Well, we want to find the number of tosses so that the probability of at least getting 1 snake eyes is at least 50%. Here's a good starting point. In fact, how do I recommend that you start most probability problems?
You would start with a random variable.
Okay. Yeah, so I recommend step 1 is to define a random variable that you're interested in. So anyone have a good idea of what event or events we could label as our random variable? That's part of the challenge. Like, so what should your random variable be?
Getting snake eyes once.
Okay. And yeah, and since we're doing multiple rolls, how about let's let SI be the event that you get snake eyes on the ith roll of the 2 die. You always roll 2 of them at the same time, by the way. When I say roll, I mean a roll of both die. That's a single roll, is you toss both of the die. What's P of S sub I? Someone who hasn't said anything yet. Good. 1 out of 36. Okay. Yes or no, SI and SJ are independent if I is not equal to J. Yes or no, folks? Cool. Okay, yeah. The different roles are independent, sure. So that's good. So about this? Yes or no, the roles are Bernoulli trials. And when I say role, I mean a pair of roles. I encourage everyone to answer. So we've got 50 folks here, so hit yes or no. Are roles Bernoulli trials? So are they independent? And is the probability of success the same on each one? And by success, I mean getting snake eyes. So yes, they are. It's the same. It's 1 out of 36 on each role. The roles don't affect each other. And finally, let's see, how about this? Yes or no? We want to find K such that the probability of SK is greater than or equal to 0.5. Yes or no? So that would be the probability of getting snake eyes on the kth roll. Well, no, that's not true. In fact, the probability of getting snake eyes is always 1 out of 36. So no. What we want to find K such that the probability that at least one roll is snake eyes of the first K of them is greater than or equal to 0.5. But i.e., that's 1 minus the probability that none of the first K rolls are snake eyes. In other words, I could write it as 1 minus the probability that the first roll is not snake eyes, and the second roll is not snake eyes, and the third roll, ... all the way up to the kth roll is not snake eyes. Okay, so that's what we want to be greater than or equal to. That's what we want to be greater than or equal to 0.5. Yeah, probability of no snakes in the first K trials. So that means we want the probability of the first K trials having no snake eyes to be less than 0.5. Now, each of them are independent. They each have the same probability. So I'll just express that as the probability of the first one but the probability of not getting snake eyes was that 35 out of 36. Okay, so we want 35 out of 36 to the kth power to be less than 0.5. Once you can get this equation, then the problem's not that hard and it becomes a pre-calculus exercise in solving for exponents, which,
So would you do log?
yeah, that's
Okay, so
that's
I
the
got
way to do it.
24.6. Would that be correct?
You got what?
I got 24.6.
Yeah, actually, that's
Okay.
right. Yeah. That ends up being the solution to this. So you would say 25 rolls. So here's how you would solve this. Well, you would take logs. Which log is up to you? I think I'll just use the natural log. So let's just take the natural log of both sides. So ln of this is ln of this, i.e. k times ln of 35 over 36. It's less than or equal to ln of 0.5. So tell me if this step is correct. K is less than ln 0.5 over ln 35 over 36. Yes or no, folks? I'm seeing some negatories. Why the negatory? Why the no? Ooh, the sign. I got the sign wrong. You're telling me that this number is negative? Yes, it is. Ln of a number that's less than 1 is negative. So yeah, I gotta flip the sign of the inequality right there. So let's make that a greater than what it should be. And there's our answer. Let's see, what the heck is that? Ln of 0.5 over, I could write it as ln of 35 minus ln of 36 is 24.6. So after 25 rolls, we'll have a greater than 50% chance of getting at least one snake eyes on those. Any questions?
Yes. So I'm wondering if we can use binomial distribution to do the same thing. So I was thinking like n choose 0 and then success to the power of 0 and then failure to the power of n.
And choose
I did.
0.
Yeah, you can be wrong.
PVN Q.
I think it's p to the power of 0 because there's no success and then failure all the time.
Mm-hmm. Yeah. Yes. That would also work. That would also work just fine.
Can we go over number 2? I just wanted to confirm my understanding. That's all.
Okay. Let's see, hold on. Did I see someone asking about the Poisson model? Yes, the Poisson model is for something that happens at random times. So the Poisson model would not apply here. In fact, the Bernoulli trials apply exactly. So you could use the binomial, I guess would be the way to think about it, distribution. There is an interesting derivation of how the Poisson model arises, which we're not going to see in this class, but it's actually a limit of binomial distributions when the product of the rate of success stays constant, but the number of trials goes to infinity. Pretty interesting. I don't think that we're going to cover that in this class, though. Okay, so what was the question about number 2?
It was just asking what's the probability that Bob wins after infinitely rolling, shooting an arrow and see who wins. And the probability of success on each attempt is 0.1. Independent.
Yeah, right. So Alice, Bob, and Charlie decide to take turns shooting an arrow at a target. They go in order: Alice, Bob, Charlie, Alice, Bob, Charlie, Alice, Bob, Charlie, Charlie, etc. Whoever gets it first is the winner. So it looks like Alice has the advantage, kind of like going first in overtime in the NFL. So there's a 10% probability of getting the bullseye on each shot independently. I asked for the probability that Bob wins this game. Okay, so what are the ways that Bob can win?
You could win on the 2nd or the 5th or the 8th or the 11th. So it's like every, I guess, 3.
Okay, let's see. He wins if it's Alice gets a miss and then Bob gets a bullseye.
Right.
Or Alice gets a miss, Bob gets a miss,
Alice gets a miss, and then Bob.
Charlie gets a miss,
Right.
Alice gets a miss, and then Bob gets a bullseye. Or miss, 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 miss. Okay, yeah, that would also be him on the 2nd, on the 4th, on the 7th. Wait.
The 2nd, 5th, 8th, and 11th.
The 5th, yeah.
Yeah.
2nd, 5th, and 8th. Yeah, okay. So, etc. So the first one would happen with probability QP. The second one would happen with probability Q to the 4th P. Third one being probability Q to the 7th P.
Yeah, that's what I did.
Okay.
And then I think we would add them up. So this, but like obviously this is an infinite sequence, so we just use that formula you showed us in the notes from a while ago. It's the geometric sequence formula, so like 1 over 1 minus r. And in this case, we can see the pattern where it starts off with, I think, 0.9 times 0.1, and everything after that is just, I think, increasing the power of q, so by 3. So you would have 0.1 times 0.9 sigma, and then inside is 0.9 cubed. Then you just condense everything into that one fraction, I believe.
Okay, yeah, that's right. All right, so adding these up, it's QP, Q to the 4th P, Q to the 7th P, ... which you can factor a QP out, and then have a Q cubed and a Q6, which is still a geometric series with Q cubed being the common ratio. Right? So yes, that's like your R in this formula now. So yeah, it'll be 1 minus Q.
Nice.
Q. And that's 0.1 over 0.9. Let's see, success is 0.1, so Q is 0.9.
0.332. Yeah.
Hey, okay.
Okay, I got that answer as well.
Wow, it's really close to 1/3. I'm surprised. Like the probability is, okay, you know why? You know why it's so close to 1/3? Because it's really unlikely that the person that goes first has much of an advantage, because it's unlikely that they get the first shot, because because the probability is only 10%. I thought maybe Alice would have an advantage, and she would. It would just be very small, because she has to like win on her first shot in order to, well, take advantage of her advantage. But as soon as like everyone's gone, then the advantage bestowed upon the person that gets to go first gets nullified. Yeah, so it almost doesn't even matter who went first. Almost. Okay, so that's it, folks. Any questions?